my name is Selim Günay, as Amarnath mentioned. So yeah, I basically want to pick up from this last point in the survey. And for those of you who are not familiar with NGA, or as a refresher to those of you who are already using NGA, I'll quickly go over what the interface looks like. And this is a screenshot from NGA West2 database interface that we use to search for ground motions. Those are examples in the fields. So quickly to go over them, the first one is the record sequence number in the NGA database. Each ground motion has a unique record sequence number, which is already documented in the flat files. So if a user knows that, you can use directly that to search for the motion. So it's possible to search for specific earthquakes, that has been referred to also as historical events multiple times, such as Loma Prieta, Kobe, Northridge, Christchurch, etc. So if you are interested in a particular station, such as Berkeley, Lawrence Berkeley National Lab, because we are basically having the workshop together with LBNL, or several famous, stations such as Rinaldi or Takatori and so on, you can directly search for the station name and find the corresponding ground motion. It's possible to basically, I know I wanted to get the mouse.
Oh, that's a different computer.
Oh, okay.
Just use it.
Okay. Okay, so let me try to use this. So basically when we get to here, you can basically search for earthquakes that occurred on a specific fault mechanism, such as strike slip, normal, reverse, etc., or search for ground motions in a certain magnitude range here. We can use distance, particularly the Joyner and Boer distance, or the closest distance to the rupture surface, as another search parameter. So it's possible to search for motions at different soil types using VS30. And you can also search for motions with specific durations using the significant duration parameter. And this is useful for searching for long duration motions and any motion of interest, basically. Yesterday, Maha Kenavi had this great presentation about pulse-like records and non-pulse-like records, and potential issues with classification of pulse-like records in soft soils. So for those type of research, you might want to use pulse-like records. So there is an option to either download pulse-like records or non-pulse-like records. Basically, this is a quick list. When the search is completed and motions that satisfy the search criteria are selected, they are listed for download by the user. But in addition to that list, the response spectra is also plotted. And these are the options here, mainly to plot the response spectra. You can choose to plot the response spectrum of an individual component, one of the two horizontal components or the vertical, or the square root of the sum of squares of the two horizontal components. You can use different damping ratios. And so particularly when people select ground motions that would match a target spectrum, it is convenient to compare the target spectrum with the average of the selected motions. So that's why there is this average with this thick curve there. And in addition to that, there is that average plus standard deviation, average minus standard deviation. So then this last option basically allows us to use either arithmetic mean for the average or the geometric mean. So yeah, this is basically, again, this was a quick review of the interface. And as we have seen from the survey, and as mentioned several times today, there is obviously an interest to keep the simulated ground motion interface similar to NGA, which is obvious. But on the other hand, there are inherent differences between a recorded ground motion data set and the simulated ground motion data set, which needs to be considered to add specifics of simulated ground motions in the interface. So to be able to do that, first we need to figure out what are the differences between a recorded ground motion data set and the simulated ground motion data set, such that we can figure out what we can exactly keep the same and what we need to add for the specifics of simulated motions. So that's why in these next 3 slides we are comparing basically recorded ground motion data set with a simulated ground motion data set, and here particularly the comparison is in terms of earthquake and station characteristics, and we are doing this comparison in the 3 common categories of source, site, and path, the source to site. So starting with the source, we mentioned you can use fault type as a search parameter in NGA, and this is completely valid for the simulated ground motion data set. When we come to the earthquake, obviously we mentioned this is a real event in the NGA, and this real event is replaced by a scenario that is that includes the combination of a region and realization in the simulated ground motion data set. For example, San Francisco Bay Area is the region, and realization 1 from that region, which Arvind talked about in detail today. And here I quickly want to mention why we have, this combination here. We obviously need the region because, as we heard through the presentations in these 2 days, the physics-based ground motion simulations require the fault rupture modeling plus the wave propagation along distances. So you need to mainly model the geological and geotechnical, geomorphological aspects over regions. And as an example, in David McAllen's presentations and Floriana's presentation today, we have seen the areas of simulations with sides in the orders of, multiple hundreds of kilometers. So what that means is inherently when you are doing physics-based simulations, you are doing it in a region. So that's why we have the region here. And there were these questions about realization yesterday. And so in the scope of how we define the realization here is basically a realization is defined by the fault rupture parameters and the simulation parameters. So the fault rupture parameters are those that were discussed by Arvind in detail today. And the simulation parameters are the minimum shear wave velocity that you resolve in the computations and the largest frequency as examples. So that is basically related to this aspect. Moving on to the source to site, we mentioned we can use Joyner and Bohr distance or the closest distance to rupture surface. So again, that is valid in the simulated ground motion data set. And yesterday, in the presentation of Brandon Bradley, he mentioned this interesting aspect of the ergodic nature of ground motion selection when you are selecting motions from a recorded ground motion data set. And this is not, as we have heard today, this is not an issue in the simulated ground motion data set, mainly because at a particular point of interest that is defined by a latitude and longitude, in a simulated ground motion data set, you may be able to choose motions from multiple realizations. So what that means is latitude and longitude becomes important search parameters in the case of a simulated ground motion data set. And we heard from multiple presentations that okay, in the simulated ground motion data set, there are subsurface motions in addition to the surface motions. So depth is another parameter. So in terms of the site, we mentioned VS30 is used in both simulated and the recorded ground motion data sets. For the location, In the recorded ground motion data set, this obviously depends on the locations of ground motion recording stations. In the case of the simulated ground motion data set, the data is stored in grid points, which is defined by mainly fault direction and spacing. And to elaborate on that aspect here, in terms of ground motion characteristics and directions, this is just a sketch that shows the recording stations from the Los Angeles area. Again, these are physical stations. And in the case of simulated data set, we have the grid points that Hojun showed in his interface. And in terms of the data, we have seen that users want acceleration, velocity, and displacement. And obviously, we have the three components, which are two horizontal components and one vertical component recorded in NGA. And those are computed in the simulated ground motion data set. In terms of the direction of the horizontal motions, in the case of NGA, these directly depend on the sensor orientation, the orientation of the accelerometer, and these orientations may differ from station to station, so they are not the same and consistent for all cases. In the case of simulated ground motion data set, each grid point have the same directions, and these directions mainly depend on the axes that you use in the simulation domain, but the two common axes are fault normal and fault parallel because of the, the reasons that we heard yesterday about the rupture directivity effects and the fling step and so on. Also we saw in the survey that users are interested in keeping the PEER format in the data files, and that's what we are directly addressing that interest, and we are keeping the same format of ground motions in the simulated ground motion data set. And what this means is the users can directly use their processing codes without a need for change to basically use read from the simulated ground motion data set files. And so my last comment here is related to the data file names. And again, if for users who are processing the files with codes, it is always meaningful to have some organized file names. And here in both NGA and the simulated ground motion data set, the file names are self-descriptive, and they include the earthquake name, here the name of the actual earthquake, and the region realization combination here, the location of the ground motion, which I'll get to in a second, the direction or the component, here this is measured with respect to north, and in the case of simulated motions, it's fault parallel, fault normal, or vertical, and the extension indicates whether it's acceleration, velocity, or displacement. So for the station, in NGA, obviously, it's a physical station, and for the simulated motion database, we are representing the location by its indices in the grid. So here you see three numbers. The first one represents the index in the direction parallel to fault. The second is normal to fault, and the third one is along the depth. So for example, 111 corresponds to this very first corner point at the surface. So I think I give it back to you.
Thank you.